Yeah, should we do it now or should we wait for everyone to join?
I mean, we can wait like 3 more minutes and do it at 10, which is what we sometimes do when we are waiting for people.
Sounds good. Yeah, I'm fine with that. I'll wait a couple minutes.
Okay, I already started the recording, but doesn't matter. People can skip a bit, I guess.
This is the AI gets stronger. It looks so. Just ignore the I should remove that. Right? Ignore the. Okay, wait. Actually, okay, I'll show you this. This outlier. I also have to do this.
We can't hear you, Josh.
Okay, should we start it? Just introduce ourselves. Sure. Seems like reasonable time, right? Yeah.
I think
All right. Sure. Yeah, I'm Josh. I'm a PhD student at MIT. I work with Max Tegmark. I work on mechanistic interpretability, AI safety stuff.
Yeah, I'm Subhash. I'm a master's student in the Tegmark group. I did my undergrad at MIT in physics and computer science, and I went to Mech Interp recently. Josh and I did this project together in Neel Nanda's math stream. I'm sure we're going to talk about it later, but we studied Sparse Autoencoders are good at doing probing as a way to evaluate them on like this like grounded interpretability task, and we got some like dubious results, which
Negative results.
yeah, negative, strong, like not dubious, I guess, like certain negative results that we're excited to talk about.
Yeah. Yeah. Cool. So how does this usually work? I regret to say I've never actually been in one of these reading groups. So I don't think we prepared a presentation or anything. So I mean, we're happy to like answer or like how do you guys usually run this?
It's fine. So,
do
sorry.
you want to go before? Yeah, go.
Basically, when we have the authors sometimes they have presentations, sometimes they don't. They just talk about the paper. Like you can share your screen with your paper, for example, and talk about it a bit.
Yeah, that sounds good.
And that's basically, and then you do that for a bit, and then people ask questions. That's how it usually goes.
Okay. Sounds good.
Should we pull up the paper?
Yeah. We can share this. Let's share the screen. Yeah. Let me just pull it up. 1 second. Up here. Oh, this is not it.
Should be on your website. Oh, there it is.
There it is. Okay, I'll just close everything. Oh, I have to open system settings and allow it and then probably restart. So give me a second. Yeah, I'll be right back. Back, and I will share now. So I'll just share my whole screen. Sure, go live. All right, can you guys see this? Oops.
Yeah.
Full screen and
Maybe you could like zoom
more.
Yeah. F11, I think.
F11? I tried F11.
Are you pressing the F10 button?
I just press 11. Wait, maybe up here. This. Where is it? Sorry, guys. I promise I'm not.
Next to the Zoom,
Oh,
next to the Zoom, there's like
Oh, here's Zoom.
no,
Next to
no.
here.
Where you were,
Yeah, yeah.
there's like four corners.
Yes. Oh,
It doesn't
that
work.
didn't work. That just made it. Maybe I'll press it again.
I think that's because you're already in.
There we go. Good. Sorry, guys.
Well, doesn't matter. That's okay.
I'll
This
try
is
one more
okay.
time.
Probably, yeah, it doesn't matter.
Okay, I don't know why it's not working. Sorry, guys. Okay, you'll have to deal with the top parts. Okay, so yeah, I guess we can just kind of go over the kind of the main experiments and results in the paper. But yeah, feel free to jump in at any point with questions. So yeah, I'm kind of assuming everyone's familiar with what sparse autoencoders are. Is that the case? If you're not, feel free to interrupt me. Or just feel free to say so, and I'm happy to explain how they work. But basically, sparse autoencoders just take in input activations from a neural network, project them up to a super wide layer, and add like a sparsity penalty, so only a sparse number of these can be active at a given time, and then project them back down to try to reconstruct the original inputs. And the idea is like you're trying to rediscover like the true like model, like the true like latents that combine together to produce the model activations.
And I guess the theory here is like we have this idea of the linear representation hypothesis that many features within models are linear. But there's also this idea of superposition that like within activations have many linear features. So sparse autoencoders allow you to project up to this super wide space where you can have all the features you want, but you combine like linear combinations of them that are like relatively sparse that happen to be very interpretable. So SAEs have been like very common, or like maybe like the hottest topic in Mech Interp over the last year and a half. But I guess like, Josh and I like started on this project because, a lot of people measure SAE progress through measures like, downstream cross entropy loss or reconstruction error. But ultimately, like we're really trying to figure out if SAEs are useful for interpretability. In order for SAEs to be useful for interpretability, they need to be useful on a task. Like they need to be useful compared to baselines on a task that we care about. So like the purpose of this study was like we care about this task of probing. Probing is a very well-established task in machine learning, and especially in interpretability. And like the central question here is, are sparse autoencoders useful? And by that, we mean, can they beat out baselines?
Yeah, and I guess it's important to also think like do we expect like if you didn't expect sparse autoencoders to win on probing anyways, then the fact that they don't win on probing is like it's not so much of an update. But for like a couple of reasons, we expected SAEs to help with probing. First, like there was some prior work showing that maybe it helped a little bit in some settings. And also, our intuition was that SAE latents are like kind of like true, like should be like more interpretable, like more true model variables. And if this is the case, and we have this kind of like more interpretable like basis, then if we use this basis and inductive bias for our probe, we tell our probe, you can only use 2 or 3 or 4 of these latents at a time. Then hopefully like requiring the probe to do this will help in some situations where like learning the normal probe is very hard.
Yeah. So I guess like intuitively, it's not super clear to me that SAEs should beat baseline probes in like normal conditions. So like let's say you have a ton of examples.
Which we find they don't here.
Yeah. If you have a ton of examples and like everything is balanced, all your classes are balanced. We're only talking about binary classification in this study. SAEs are naturally like they have loss compared to normal activations. So baseline probe applied to normal activations has strictly more information. Well, maybe not strictly, but it has more information intuitively than SAE activations do. But I guess the question is like, if there's some magic like inductive bias in the latents of SAEs, then as we go to these like really difficult regimes, like if we have very little data scarcity, or we have a huge class imbalance, or we have a ton of like corruption in our data, or we go out of distribution, like that inductive bias of SAEs having meaningful latents should help us in these different regimes. So that was like the hope of our study, the optimistic case for SAEs. But I think ultimately we found that SAEs actually didn't help, even like no matter how hard we made the regimes or what regimes we tested in, they were not differentially useful over baselines.
Yep. And kind of we'll kind of get into more of the like nitty gritty of I guess of our experiments. But I guess one other takeaway we had was that it's really important to have like to when you're comparing your baselines, trying to beat baselines, to like be really careful with your baseline implementations, because like there were a couple times we kind of tricked ourselves and thought that SAs were like actually like good for like this task, and then it ended up that they weren't.
Yeah.
So maybe before we go on, do people have any questions about kind of like the setup and our like main findings?
Well, I don't know if this is jumping too ahead, and just ignore my question if it is. Like on the like finding dark matter of essays, or I forget exactly the name. The fact that there's so much to be explained by current essay techniques, or maybe like forever, even if we improve the architecture.
Yeah.
Do you think that that's what's harming the performance of here, or do you think that maybe if there was no dark matter, maybe you wouldn't expect them to ever match up?
Yeah, it's a great question. I think a lot of this is not just the fact that essays are losing information. Like, certainly, like if you train on a lot of data, like in standard conditions, I think this gap is mostly due to dark matter. But I guess it's possible the gap in other places is also due to dark matter. But like, the hope is not that like SA probes do equally as well as the original things. Like if you have like any sort of perfect reconstruction, then probably it'll do equally well. The hope is that you do like much better in some cases. And I don't think that like dark matter, like not learning many features, should like significantly impact like the features you do learn. If SAEs were working really well, hopefully the features the latents you do learn would help you like do much better on some data sets. In like some settings.
And I guess some like ground intuition here is like if we look at a specific example of out of distribution data. So like, one of our tasks is like, can you identify if a sentence has the phrase living room, right? So we found there was an essay latent that was like that really fired strongly on living room, and like it like had like a very, very high AUC. But once we went out of distribution, if we did living room in a different language, that essay latent would no longer fire. So that's, in my mind, that's like a flaw of like the essay latents fundamentally, is that like, this latent is not perfect. It's not actually representing the concept of living room across languages. It's instead just like representing it in one language. So in some sense, like that points to me to a flaw of SAEs, which I don't think is related to dark matter. But I think like an interesting thing in this regime is like, you bring up a good point that it's not clear to me that SAE should beat baselines because of dark matter. But our most negative result, or my most negative update, was that subsequent SAE architectures don't actually improve on probing, which is like very negative. Like you would expect, like even if SAEs don't beat baselines, they would get better throughout time as we make SAE architectures better. But unfortunately, we don't find that.
Or if you make essays wider, we also find that wider essays like have like lower variance explained, but they don't really improve on probing.
Yeah.
Another thing is that like I think this kind of like I'd really be excited for works that optimize SAEs for things besides like downstream cross entropy loss or like variance explained. Like it'd be great. I would think it's even better if someone says this at the same variance explained, like we have like way more interpretable latents, or like way more robust latents that are like way better for outer distribution, or like this sort of thing. That would be really, I think that would be like big progress.
Yeah, I guess like that's the ideal. I think it's hard because like interpretability has these subjective ideas of what makes interpretable features. Like that's naturally difficult to quantify in a way that cross entropy loss is not difficult to quantify. So it makes training these things harder. And I guess that's why the field has relied on proxy metrics like reconstruction errors so far. But yeah, I guess like our big message is that we should consider different metrics that actually are aligned with interpretability and aligned with the things that we care about as Mech Interp scientists.
Yeah. Any other questions before we go on? That's a great question.
I think Ned like wrote a question on the chat, on the reading group.
Wait, can you read it out? Because I don't want to.
What's an example of a task where it's very hard to train a linear probe?
Like a standard linear probe. I think that so. Like one place is like so you can see here. This is like the average test AUC in like these different settings, and like I guess if you just have like a probing data set, but you have like very, very few examples, it's hard to train a linear probe that will get high test accuracy. And same with like if you have like a lot of noise in your labels, it's also very hard to get
test accuracy. Like you corrupt some of the Y values.
Exactly.
But I think so those are problems with like how many data points you have, or like the form of your data set. But I think there are sometimes like intrinsically difficult data sets to probe with. So one example that we have in this paper, maybe it's a little bit too far down, but one example we have in this paper is if a headline is on the front page of a newspaper. So these are both headlines from newspapers, but one of them is from the front page and one of them isn't. It's actually like not super clear to me how you would figure that out with the probe, and like even baseline probes do very poorly on this task, like 0.65 AUC. So like one of the focuses of our project was, making sure that we don't have street lighting effects, like making sure we take really difficult data sets that should be very challenging for both binary probes and SAE probes, so we can like really fairly evaluate SAE probes.
Yeah, I think one fair criticism, I guess, that I think about some of the times about this work is that like this data set, like if you're actually doing probing, you would never actually probe. Like the interesting probes are not like, is a headline the front page. Like in practice, interesting probes like, is the model deceiving you? Like is the model being honest? Does the model know it's in a benchmark? Right? Is the model self-aware? And I guess kind of one of the things of our work is that hopefully we choose a very large variety of probing data sets, and then like just like generalize well like these other types of like more interesting problems.
Yeah. Are there any other questions?
Okay, let's talk about our methodology. So basically, when we're training probes, what we do is we take like all the activations from like class 0 and class 1. We pass them through the SAE. And then we choose like the K latents that have like the highest average difference in like across the two classes. And then we train a linear probe only on those K latents across like all the examples. And then to see if like this method actually is better than just existing baselines, we do this thing called we call like the quiver of arrows approach, where we run all of the methods and then choose the best method by validation AUC, and then return the test AUC for that method. And then we do that with the SAE probe and without the SAE probe. And the idea is that like we're trying to see whether like adding the SAE probe, the arrow, to the existing quiver of methods actually improves performance.
Yeah, I guess the intuition here is like, want to model how well a practitioner with SAE probes is compared to a practitioner without SAE probes.
Correct.
So like what Josh is kind of describing is like you have one practitioner that just has these baseline methods like KNN, MLP, XGBoost, whatever. And you see like how well they do on test AUC given you choose the best method of validation AUC for each data set. And now you like simulate another practitioner, the same arrows, except they also have SAE probes. And if SAE probes like actually help, they improve test AUC robustly, then that means that like SAE probes are actually a very useful addition to a practitioner's toolkit. So that's the intuition.
Yep. Questions about that?
I have one. Maybe it doesn't make sense, but I'm wondering if you, instead of using all latents that could be active, if you use just like, let's say, top 1, top 2.
Yeah.
Because maybe the ones that are active but have lower activations are maybe distractor.
We do select the top K by the average latent diff, if that's what you're saying. And down here we compare like as you vary K, what happens to the test AUC. And so we find that like basically once you have like look at like the top K, like 32 or 64 latents, you pretty much do as well as you're ever gonna do.
Okay, I was actually wondering the other way around, that maybe having too many latents active, per example, could maybe be distracting in the sense of having like spurious correlations or something.
Oh yeah,
spurious correlation.
Yeah, we actually examine that a little bit later, where we like we take a probe with like K equals 8 or something like that, and we try to prune down features that we feel are spurious, and we see if like performance improves. The results for that are like marginal. I think like you can sometimes get some improvement. I think like this is a trade-off. Like if you wanted to just like mimic baseline or mimic activations, you'd use K as large as possible, just to like get the closest thing to what baseline activations are. But like we use like k equals what, 16?
Yeah, 16 and 128.
Yeah, k equals 16 and 128 in order to like kind of like diminish this like spurious correlation thing.
Yeah, I think k equals 16 is closest to this regime you're saying, where like you want to like ignore spurious correlations. You're still training like just regression probe on the 16 latents that you choose, and so like the logistic regression probe can decide, and that regression probe is still normalized. So like that probe can still decide like not to pay attention to one of the latents.
Right. Okay.
Yeah. But I agree. Like there is so in the appendix, like way down here, we have like the performance of the top, just like one latent. This is this is number of features in 1, 2, 4, 8, 16. So you can see like how good one latent is and like how it kind of jumps up each data set. And on none of these data sets does it really go down. Like it never really hurts to have like
More information.
More information, pretty much. Like maybe like here I guess it goes down a teensy bit, or like in a couple places, but for the most part it basically only ever gets better as you have more information for the SAE. Yeah. Go back up. Sorry, was there something, another question?
Hi,
Yes.
I have a question about.
Go ahead, Jonah.
Okay, yeah. Hi, I was about to ask about the quiver of arrow method.
Sure.
As I understand, this method only can prove that adding the side probe to the as an arrow, it will give you a better result than the other methods, right? You can't prove that it is worse than the other one, or it is similar, right?
Oh, you're saying that like if you add SAEs to the quiver, it will be at worst just as good and never worse. Is that the intuition you have?
More or less, like you can prove that, as I understand, when you add the side, it is not worse than the other one.
No.
It could be similar or far worse.
You'd think so, but actually it can be worse because, so if you were choosing, let's say you had this quiver of arrows with 5 baseline methods and you were choosing the best one on test AUC, then as you add SAE probes in, if you're just choosing based off test AUC, then you're guaranteed to be at least as good. Because like the metric you care about is what you're choosing with. But the problem is we're choosing the best method of validation AUC, which is it's intrinsically noisy. So you can imagine this world where like, maybe when I add the SAE probe in, the validation AUC goes up, but the test AUC of the SAE probe is actually worse than the best method from before. So in that sense, you can get negative results. And in fact, we find that in almost every regime adding SAE probes
Basically,
is worse.
if SAE probes perform the same, approximately the same as the other methods, then adding it should make things worse on average, just because of noise in the validation. Or like if it's like a little bit worse, let's say SAEs are like slightly worse.
Yeah.
If SAEs are slightly worse, then
Yeah.
you would expect them, and they had like if the SAEs were just constantly slightly worse, and you add them to the quiver, then it would make things worse. We also do compare on like test AUC, for example. This is just comparing straight test AUC, no quiver, and then it also makes the drops more clear. Yeah. The reason that we're interested in doing this quiver thing also is that like we were thinking maybe SAEs help on some data sets and not on others. And if you can identify the data sets they help on consistently, then you could still see an improvement.
Yeah, but we didn't find that. We actually we just wanted to make the steelman case for SAEs. Like we started just comparing on test AUC, we didn't see any improvement, and we were like, okay, the quiver of arrows is like the most helpful thing we could do for SAEs. So we can see some improvement because of SAEs. But even when we tried to make SAEs win as much as possible, they just wouldn't win.
Yeah. Any other questions about methodology?
Yes. So I don't really understand this quiver of arrows. What is the difference between this and just checking if it's actually better than the other methods?
So
Because
the problem, like in some of our settings, right? So like let me scroll down here to, this might make it more clear, to this plot. So if you look at this plot, right? This plot plots for like different settings. Like here, this is like corrupted. This is like classic balance. This is like data scarcity. If you look at these plots,
Wait, so just to be clear, the y-axis here are different data sets.
Yeah.
And then as you move across the x-axis, you're increasing like, here it says fraction corrupted. So this is label noise. You're increasing like how much label noise there is, or ratio positive
the class, you're increasing the class imbalance. Number of training examples, you increase the number of training examples,
Right.
you decrease scarcity.
Right. So if you look at this plot, right, you see a lot. So blue here means the SAE improves. And so if you look at this plot, you say, oh, like the SAE improves a lot. Like it's probably a pretty good technique, right? And so that's kind of like why this is like the case where like maybe SAEs help. But what happens is that if you choose the best method based off the validation metric, then this plot basically turns like all red. Like the average, like you don't, on average, you don't improve. So the idea is you can't extract the juice here. You can't get the blue without also getting the red.
Yeah, I think intuitively it's like, when you test a bunch of hypotheses and statistics, like you're just gonna have one that works naturally because you're testing like a million of them. So if I tested a million SAEs against like 3 baseline methods, like because of random luck, because of variance in SAEs, like maybe one of the SAEs will have a test AUC that is higher than baseline methods, and we can say, oh yay, SAEs work. But you want to be able to choose the best method before seeing the test data set. So you need to choose off validation AUC. And if you can't successfully choose the best method of validation AUC that has the highest SAUC, then the method is no good. Yeah. So like the quiver of arrows like really make sure that like, are SAEs useful when we're not cheating by looking at the test set? When we're just looking at validation AUC, can they lead to an improvement in test AUC? Does that make sense?
So it would be, it doesn't lead to an improvement if it leads to an improvement only in the validation set.
Like it needs to, if it's going to lead to an improvement in test AUC, it needs to also lead to an improvement in validation AUC in order for this to be useful. Like if our SAEs will sometimes have a better test AUC, but will always have a worse validation AUC, like no practitioner is going to use that, right? Because you're just finding variance at that point. You really want to have a method that has a consistently higher validation AUC, which leads to a higher test AUC. And basically, we don't find.
And the reason that this is hard is like, for example, in data scarcity, you just don't have that much data to choose. Like your validation AUC basically comes from cross validation. In the noisy case, your validation data set is like actually noisy. So like it's hard to actually choose the actual best method here.
Okay.
And you can't just. We also tried to just choosing always SAE, and that also performs worse. Yeah.
Okay.
So
I think I get
you ready? Okay. Cool. Okay. Let's move on. Let's talk about some of our results. So first, we mentioned this result: as you increase K, the probes get better. This is basically just saying that in standard conditions, SAE probes perform worse, as we expect. These plots, I'll kind of go through these a little bit fast because there's more interesting stuff at the end, and this is kind of staying where I said. Basically, just saying these just show like when you add SAEs to the quiver, like these show the solid line is without SAEs, right, and the dashed line is with SAEs. And you can see that when you add them to the quiver, it doesn't really change that much either on specific data sets or on all the data sets. And those are the main results here. This is like, you want to talk about this result?
Yeah, these are some well, first, did everybody understand these results? Basically, like, I think the most important plots are maybe these, like on aggregate, if we look at across all data sets, SAEs, when we add them to the quiver, are like slightly negative. I mean, they're definitely not better, and it's within the margin of error here, the 95% confidence intervals, but very clearly, like, they don't lead to like a real significant improvement. So I guess like these are for the regimes of data scarcity, class imbalance, and label noise. Now, if we move to the regime of OOD data is a little bit hard to make because like it's like bespoke. So for example, we had this one data set that was like, can you identify if a historical figure is a male? So we did instead is like we made a data set of fictional characters like Mario male, like Luigi male, etc. Similar, like we had this task of is Social Security inside the text, the prompt, and then we tested if those same probes would work when we translate the sentences to Spanish or something like that. And you can see that the red curves, the red lines here are the AUC of the baseline method, and the blue curves are, or the blue lines here are the AUC of the SAEs. And aggregated across all data sets, this is a smaller sample size to be sure, but we still see that baselines are better than SAEs, which honestly, that was a little bit surprising to me. I didn't think that baseline probes are going to be very good when you go out of distribution like this, but they seem to outperform SAEs.
Yeah, logistic regression is really good.
Yeah, I think like a big lesson for us is that logistic regression is like extremely good, strong baseline.
Yeah, we also use the sklearn logistic regression. So this is like a possible foot gun in that if you implement your own logistic regression, in PyTorch using gradient descent, it'll probably be not as good as like the optimized sklearn implementation. So just something to keep in mind. Yeah. Okay. Any questions here before we kind of go into like our like next set of results?
Yeah, I have a question.
Go.
Go, please.
You go first.
Okay, thanks. I see that the 100 or something dataset that you use were only text-based, right?
Yes.
Do you think your results generalize to other kind of modalities like audio, images, or some kind of other networks?
I don't know. Do SAEs generalize other modalities?
They do. There are multimodal SAEs. Yeah, I don't know. I don't. Yeah, this is just text. I really don't know what would happen with images. I kind of think it would be similar.
I think it'd be the same.
Because it's a problem with SAEs, not a problem with the data.
And probes started, the Bengio paper, the original Bengio like probing paper was on images as well. I think like logistic regression would just be a very strong baseline there as well. But this is intuition. I don't think we have any evidence to back up our claims here.
Yeah.
But I can't imagine like SAEs are bad on text and then they're like better on images. It feels like they'd be best on text to me.
Most SAE research does use text. Just for like, I think most open source, like the Jamascope SAEs that we use here, are just on text. There probably are some open source SAEs on multimodality data, but I'm not even sure exactly what those are.
Yeah. Any other questions before we move on?
The multiple language example that you gave, that some like a specific latent would fire on multiple languages, but maybe it wouldn't fire in French or something. Have you covered that already, or is that afterwards? It's afterwards. Okay, so let's
actually.
We can talk about it now.
Yeah, it's a little bit related to our we were trying to figure out like why in OOG settings like why don't probes work well. So I think we had a few hypotheses. One hypothesis is that the underlying latents themselves are not good enough. So yeah, here's like latent 12.122.774. So this latent is really good. It has a AUC in English of like 0.99. And you can see like when we just we run literally the phrase living room on this latent in a bunch of different languages, we see that it fires very strongly in English and it fires in a lot of languages actually. Weirdly, it doesn't fire on French. And it's not, we didn't actually cheat to get this result. Like we just happened to test it on French. So like maybe a little bit of bad luck. But it's kind of likely to me as well that maybe if you run this latent on really long contexts, maybe it only fires like consistently on English. This is like the best case result when we just run on the phrase living room. So like one hypothesis that I think we have some evidence for is that like SAE latents aren't very good right now. And I mean, this isn't like, I don't know, it's like nobody thought that this would be a super multilingual feature in the sense that like the original Jamascope SAEs that we base our study off of were primarily trained on English and they were upfront about that.
But the hope would kind of be that like if the SAE is discovering like true model variables, like the true features models use, like those are obviously multilingual. So like the hope is that SAEs would discover those.
Yeah. And
it kind of seems like they're not doing that.
Yeah, but I guess we can start talking about this like interpretability section where we look at our results and like understand like why things shaked out the way they did. So, even if probes are worse, like SAEs are an interpretability technique, so we should measure them on interpretability tasks. So there's a few things we can do. We can measure, we can try to understand why SAE probes to fail by doing probe pruning, kind of like a previous question asker asked about like, oh, what about spurious correlations? And probe pruning kind of tries to target spurious correlations. There's latent interpretability, which is like where we can like automatically try to find spurious latents, or like get rid of latents or understand latents by like looking at their Autoencoders scores or like understanding what they fire on. And lastly, there's like detecting dataset quality issues. So this is like really exciting in that like previous work has found that, by using SAE probes that are naturally interpretable, we can find spurious dataset features. Like, maybe certain datasets have this tell where if the target is 1, then the prompt always ends with a period. And if target is 0, the prompt always ends with the exclamation mark. And we actually find something similar to that. I think like our results here, let's just go through them. But I think what we ended up finding is that even though you think that SAEs would be differentially useful on interpretability, turns out that baselines are able to do a lot of the same thing if you make your baselines really good, which again is the theme of our work.
I do think that like we do have like some like mild evidence that maybe like there might be tasks where SAEs actually could perform really well. They just like in our cases the spurious correlations were like all pretty obvious. But if you have like less obvious spurious correlations, I think SAEs could maybe win out.
Yeah.
Yeah.
So I guess we can talk about probe interpretability now. So there's two parts to probe interpretability. One, we want to look at pruning. So like, I guess like we just want to understand why SAEs fail to generalize OOD. So there's two things: either latents the latents SAE probes rely on leverage these spurious correlations. So the intuition there is that if that was true, then you should be able to get rid of the spurious correlation latents and improve your probe. And the second thing is like maybe the latents just aren't good enough. They're not robust to distributional shift. So hypothesis one, investigating if there are spurious correlations that we can prune out. Basically what we do here is we focus on 3 data sets. And for each of these data sets, we create like a k=8 top latent probe. From there, we like look at the 8 latents and use like 3.5 sonnet to generate descriptions for each of the latents using like very standard, Autoencoders stuff. Then what we want to do is we want to get another model, a smarter model, to be like, okay, these are the latents. I know what the task is. Are any of these latents like not useful? Would cutting them out, would cutting any of these latents out actually like improve probe performance? So in some sense, this is kind of a system test. You want to test the latents, but you also want to test Autoencoders to see if like Autoencoders could actually tell us something useful about, what latents are useful, what latents are not. So like given all the latents for like, the task of identifying if living room is in the phrase or the phrase living room is in the text, we give, a description of all 8 latents. And then we ask it to rank them by usefulness. And, it does something, I think actually this table is worth going to. So like there's a latent that is just mentions of living room parlors. So like, O1 ranks as like number 1 and the AUC is like pretty good for this latent as well. And then like we have other things like the least important latent are like objects and materials related to scientific experiments and laboratory equipment. It's very unclear to me how that would help on a task where
it actually has a good AUC.
You're trying to identify if a living room is there. But yeah, Josh points out that there's actually a very good AUC for this latent, which kind of tells us something about, to me, this is telling us something about Autoencoders, that Autoencoders is not like good enough yet, because like, very clearly like Autoencoders is not like fully characterizing what this latent would fire on. But the idea here is like, okay, we now have all the latents ranked in order. So like now let's run a probe with just the top most relevant latent or the top k most relevant latents from this. Can we actually improve performance compared to using all 8 latents? And that like even though you're losing information, you're losing spurious correlations as well. So the intuition is that should help you by like getting rid of like a latent like number 8, which like sounds like it shouldn't be useful. Ideally, your probe will become more performant. Yeah, I think like going back to the main text, we see that there's like maybe marginal improvements when you do something like that. I don't know if I actually have that graph in here.
It's in the appendix.
No.
But yeah, I think it's pretty marginal.
Yeah, the improvement is marginal when you do something like that. I guess that's like the most important thing to show. And again, like the second hypothesis is that, if latents actually generalize out of distribution, we've talked about this a bunch, but yeah, this latent doesn't generalize out of distribution, which is another reason why OOD generalization might not be good. Yeah,
I can talk about this. I do have to go at 1, so I want to make sure I get to like the end and leave a little bit of time for more questions. So maybe I'll just kind of skip a little bit over this. Basically, this part just talks about we can like basically generate like interesting categories of latents. We can find like a bunch of spurious correlations. We can find like really interesting latents that like we kind of get a little more insight to because they're like the top classifier out in like a data set. So like here, another thing is like incorrect Autoencoders labels. Like you can kind of realize the Autoencoders is wrong because it fires on like an Italian data set. But like the description reads names of researchers and scientific authors. So just kind of like you can get some insight by using probing data sets. And then another thing, I'm also going to zip through this a little fast. This was something where we were excited originally about SAEs. So we thought SAEs could identify. So if we thought SAEs would identify spurious correlations really well. So we found that like when we looked at this data set that the latents that were the most important were periods, fired on periods and spaces. And indeed, when we looked, the last token in the examples were like periods and question marks and spaces. So this is a Sparse correlation that we identified. However, it also turned out that if you just train a logistic regression probe and then look at its dot products with like all the pile, like all like activations from the pile, the highest activations are also punctuation. So this is like a different method that would also reveal that you had a Sparse correlation.
Yeah.
Yeah. And then do you want to talk about glucola?
I feel like it's worth skipping over if you
Okay.
want to get to.
Yeah. Okay. So then the last couple of things I think that are interesting. There's like one more result here, but it's not basically the same sort of thing where we thought that SAEs would be differentially useful, but it turned out baselines could do it as well. So one other thing we report here is we look at multi-token probing, which prior work had found like SAEs that were differentially useful on. And we also find that it does, when we do multi-token probing, SAE probes do get a little bit better. But the problem here is that if you don't compare to a sufficiently strong baseline, you think SAE probes are like better than they actually are. So if you just compare to like last token probing, then SAE probes seem like they do really well, like they win on like a very large fraction of data sets. But if you do this attention-based probe, where you first basically for the first thing you do is you train one linear probe that dots with each token activation, and then do another linear probe that dots with each token activation, and then weight the scores of the second probe by the softmax of the first probe. Then like these like more naturally multi-token probes like basically make SAEs win a lot less.
Yeah, I guess the importance here is like if you have this like smarter attention-based like probe baseline, then like you like lose this illusion of SAEs winning. So like ultimately, like I guess you noticed it with like interpretability and now with like multi-token. If you just like are thinking about improving your baselines as much as you are thinking about improving your SAEs and your target method, then like now we're doing like real science where like you can be very rigorous with your conclusions. And we still do find that SAEs do improve when we move to multi-token compared to when we were just working on the last token. Yeah. But it's just important to be very fair, I think, with making the baselines as strong as possible.
Yep. And then the last result, we basically look at like across SAE architectures and find that like there's not really any improvement over time.
Yeah, this is a very negative update for us, I think. Like it's just very sad that you think that, even if SAEs can't be baselines, that like, if they're getting better in any meaningful way, that they should improve over time. And I guess there's like a very, very slight uptick, but it's not even significant compared to the variance in data here.
I guess my conclusion is basically that like SAEs don't seem like they're very useful for probing difficult conditions. Yeah. And like they're not really getting better over time. And like this just seems like a task where they're not good, which fine. SAEs don't have to be good at all tasks, but like we really thought they would be good here. And it's like, I mean, it'd be really good to find some tasks where they actually are good.
Yeah, I guess if we move on to like our headline takeaways, I think like our very big takeaway is that, if SAEs are going to be useful for Mech Interp, if we think they're useful and it's not just hype, then we should be able to find tasks where they are differentially useful compared to baselines, where they actually lead to an improvement. It's fine that probing is not that task, but if there are no tasks where SAEs are differentially useful, then it's not super clear to me what the value of SAEs are past their like scientific value. And like even if current SAE architectures are not very good, like it doesn't mean that future SAE architectures aren't going to be good either. I think it's just important to like make sure that we think about very grounded interim tasks when we're evaluating this method.
Yeah. Okay. We can be done with the presentation. Just take questions now.
I think maybe sharing your screen would still be helpful. But,
still be helpful. Okay, sure.
I've asked a bunch of questions already, so I'll leave other people to ask questions first. But I have questions. So
okay.
So someone in the chat asked, the paper shows spurious correlations are not the primary reason SAE probes fail to generalize out of distribution. If not spurious correlation, what other factors might explain this drop?
It's this factor we talked about where like the SAE features are just not robust.
Yeah, I think that's part of it. SAE features are not robust, but then you can also imagine like let's say let's take the task like headline is front page. Maybe to do that task, you need like 100 latents or something like that. Like you need to figure out if this is a newspaper headline, like what does it mean to be on front page? And to do this very complex probing task, you need a ton of latents. Like naturally, by imposing a k equals 16 or k equals 128 boundary, you're like limiting the total amount of information we can have. So there's like one angle, which is like, essay latents themselves are not robust and don't have enough information. The second angle is like, we don't allow ourselves to have enough essay latents in order for it to be useful. I'm a little bit doubtful that's the reason. And the third reason is that SAEs are just like inherently lossy. Like they're not going to have all the information as baselines. And like, perhaps like that's one of the reasons they don't generalize well is because they don't learn robust features.
Okay.
Yeah, I think the biggest thing is the robustness.
This is related to the question that I wanted to ask, where this robustness and specifically the thing that you were probing for feels a lot like the absorption and the feature absorption like phenomena, which I don't know if you're familiar, where, for instance, you have a latent that fires on words that start with the letter E, but then it doesn't fire on elephant because it fires on elephant. I don't know if you've seen these results already.
I'm aware of the feature absorption. I feel like it's a little like you're saying that the features have like absorbed the common co-occurrences.
One, for instance.
Then they're not. Sorry.
So, for instance, maybe the French word for living room is frequent enough that there is a specific feature for French living room, right?
So we might hope that like Matryoshka SAEs or different types of SAEs would help with this, but when we test, do we test Matryoshka on OOD?
Yeah, I think we test it on.
Yeah,
we do.
So on OOD, I think it's down.
So I think that's an interesting result because then it either contradicts the fact that it's not only because they're not robust, or it contradicts the fact that maybe matrioskas seem to be fixing, let's say, absorption in very simple settings, but are maybe not actually fixing absorption in realistic settings.
Yeah, I think that's my intuition too. Yeah, it's just like a toy. It doesn't fix real absorption maybe.
I think specific to like the OOD example, like in this case, like if you have just like a specific French latent, you're not going to find that when you train a probe just on an English latent. But yeah, I guess the fact that you have a French latent for living room is not great in the first place. You just really want to have an abstract living room concept.
Right. But the thing is, that doesn't work for Matryoshka.
Yeah, where they have the hierarchical features.
Yeah. Like there's not like a hierarchical living room or like French and English, and then. Yeah, I think it'd be interesting to just look at, like, for example, the living room task on like Matryoshka, because it kind of gives you like why isn't Matryoshka winning on this like on language tests, right? Like if this is like one interesting thing, I guess, like another baseline for Matryoshka, like they look a lot of like first letter versus like is there like an A latent, right? But another thing would be like, is there like an English versus French latent?
Yeah,
interesting.
But I guess plausibly, like even if there is a latent for the abstract living room, and then there's also a latent for English living room and French living room, and Matryoshka has this hierarchy of features, because of how we do probing, it's very possible that like an English like probes just use the English.
I think there shouldn't be like an English feature. It should just be living room. It should just be like English and French.
Okay.
Ideally.
Yeah, I guess that makes sense. I think that Matryoshka is the opposite way, where they have living room and then cascading down.
Right. Well, the thing is, they would have like ideally you just learn all a separate concept.
Yeah.
Right.
Yeah, but it would be cascading up, right? So it would start from the most frequent firing, which would be if it's English or French, and then
Yeah, that makes
and then you would only have like living room on it in addition to English and French.
Yeah. Okay, that's good.
Yeah. So I think it's an interesting question. Why is it Meyerman? I do think OOD wise, like we could have more like future work code to get more OOD tasks. I think would be interesting.
I think it's definitely probably the most interesting section of our paper, like for the main results.
Yeah. It's also the hardest to do experiments with.
Someone else asked, thank you for your work. The key appeal of SAEs is that they are trained unsupervised on model activations and interpretable latents emerge. No curation is required. Do you have any insights toward the research direction that would be better, i.e. not requiring curation of tasks?
Yeah, I think it's actually really fair is that like, SAEs are magic. The fact that they can find features unsupervised is insane to me. And you're testing on a supervised learning task. So it's not like maybe this is like an apples to oranges comparison. And I guess like we want first there to be other tasks in addition to probing in order for us to evaluate SAEs, because like that's a fair criticism of even evaluating SAEs on probing. I don't know what ideas I have. I think we got really lucky with the idea of SAEs, and they've been very good for the field. I don't know. I don't really know what's next architecturally.
I mean, I think probing is really good. Like for, I guess, if you want to do probing, my suggestion would just be to do supervised probing. I think that's all this is saying. In terms of SAEs, like I think there's all sorts of like weird loss functions you could imagine that would still be like relatively unsupervised, but hopefully would improve downstream task performance.
Yeah.
Like there's been some work on this. Like there's this work called GSAEs that tries to use like tries to increase like steering performance by like looking at like trying to make them like more aligned, make them like have larger effects on the loss. So I think it's like possible to still have unsupervised techniques that like improve on downstream tasks. Any other questions?
Yeah, I think we got to wrap up in a couple of minutes, but yeah, any like maybe one or two more.
Yeah, if I can on Autoencoders.
Yeah.
Yeah, I mean, I'm curious on like what specific things you were looking, if you're doing like Autoencoders of the top activations, or if you're like sampling. I do agree with you that like Autoencoders sucks at the moment, especially for instance in our library. What we are seeing more and more is that maybe we give too emphasis in the prompt for the specific token that activates, which makes the kind of explanation that you were saying of artists and famous people, instead of understanding that it should be Italian artists, or instead of understanding that it should be in Italian context. And I think that that's something that should be fixed. But I was just wondering, like what kind of things you were using to do Autoencoders.
I was actually just using like the interface from Neuronpedia. I'm pretty sure Neuronpedia does top. Did she use top activation?
I don't know. They
might use percentiles or like.
They use top.
Oh, they use top.
Yeah. They probably use my library actually. I think Neuronpedia uses the Eluther library sometimes, or it can use some other library.
Yeah, I think that the default Gemascope ones used like the old implementation where it mostly does top.
Yeah.
Which wouldn't surprise me that like that you'd have explanations that don't match the full range of distribution. But I wouldn't expect that you would see like a significant increase, let's say, in interpretability, but maybe you'd get something that is a bit more coherent.
This goes into the fact that like if we had really good Autoencoders, then then maybe we could have some success here.
Yeah.
But we just don't have that yet.
Yeah. Agreed.
Okay. I think that's all we have time for.
All right. Thank you guys for listening.
Yeah.
Thank you for coming and for answering all the questions.
Absolutely.
Thanks for coming.
Yeah. Bye, guys.
Bye. Okay, I close the